This time there are not many zeros. It's all like this. And first thing we're going to do is go for eigenvalues. You know how to do that, right? It turns out similar situation. Only eigenvalue, one eigenvalue, this time is 3, and its dimensions 1, like that. So that part I'm going to skip, right? And the second part is asking you to compute this one. So hopefully this chasing is similar to what we did here. E1 is going to 0, right? E2 is going to E1, and E3 is going to E2, right? We want to have that situation. If you have that situation, if you apply 3 times, it's going to be the 0 map. They wanted to create it. So how about the first one? What are you going to do? How do we know this one exists? Is exactly the eigenvector, isn't it? V1 is eigenvector. So that's how we're going to start. 5b. This is homework 2.7, right? 6b or 5b, somewhere there. 6b is about solve this thing. M minus 3i v1 equals 0. We solved it in part A, right? v1 is really an eigenspace of 3, isn't it? This condition is exactly the eigenvector. There. Good? And second thing is that actually I'm asking you to solve this one in that problem. Go ahead and find these vectors, right? So you just do what is asked to do. So here's a solve. The next thing is a solve m minus 3i v2, and you got this v1. And v1, it turns out, it's amazing, I still remember this, 0 to 1. 0 to 1. So you put in the 0 to 1, and you're going to do row echelon reduction to solve this one, right? Do you notice that there's no unique solution to this one? When you do that, because there's null space dimension 1, there's no unique solution. So it depends your choice. Which one you ever choose, it's going to work. There's no unique answer to v2. So I'm going to write it like this. Choose v2, infinitely many, but here, what is your v2? I just did this by hand. Can you believe that? No, nobody believed that I did this one by hand. This is 1/9 and 2/1. Do you know how to find all the other solution to this v2? You add linear span of this one. That's the kernel of this map, right? This is a homogeneous equation and particular solution, general solution. Remember that part from differential equation and linear. So this is a particular solution. General solution is adding the kernel, the null space. Null space is this. So this is one solution we got. And so that's your v2. And the next thing I ask you to do is that, all right, m minus 3i. You solve one more time and pulling it back one more level like this. And what is it? And then you choose v3 to be this ugly thing, 781 and 19 divided by 9, 1. So we have this third vector right there. Then I ask you to prove this v1, v2, v3 is a linearly independent, right? And I allow you to use a lower echelon form for a calculator, and it turns out they're linearly independent. All right? Using row echelon form. What happens if you reduce the row echelon form with this one? If it's linearly independent, what does that become? Row reduction of 3 by 3 matrix. Identity 1, 1, 1 and 0, right? So it becomes like that. All right, thank you. So that's that. So what is the next part? And it is asking you to actually show that m minus 3i 1, 2 is a non-zero, but if you go to repeat the third time, the matrix is going to be 0. So rather than actually multiplying this matrix, so there's this matrix minus 2 minus 3, right? So what does m minus 3i look like? You subtract 3 is a 0, subtract 3 is a 4, subtract the negative 4, right? And everything else stays there, negative 2 and negative 8, 18 and 9 and 2. You can multiply this one 3 times and show it's a 0, right? But that trick that we pulled out is really neat. So here's here's V1 and V2 and V3. These are not E1 and E2, E3. And this is still column vectors, right? This is not abstract vector space. These are linearly independent, right? So do you see this as a basis? V1, V2, V3, dimension 3, basis. So if I know where this guy is going, I know everything, right? So it's m minus 3i. Where is this? V1 is going. You don't have to calculate anything. We already did that. V1 is supposed to go 0, right? Where's V2 supposed to go? Here, V2 is supposed to go V1. We calculated already. So this is the wonderful part. V3 supposed to go to V2. All right? That's one-time application. Let's do one more time. m minus 3i. Where does that go? 0 goes to 0. V1 goes to 0. V2 go to V1, right? Third time. Then 0, 0. V1 goes to 0, right? So you show, without multiplying this thing, all right, I checked 3 vectors, but they're linearly independent, and in enough number of them. Therefore, I don't have to multiply. It's going to be 0. And 3 is the smallest number that becomes 0, right? Those who take the algebra, this is like a multiplicative order of this is the order of this one as a group. Right? M minus 3 is 0. M minus 3, 2 is not 0. There's 0, 0, but hey, there's non-zero map. 1 is definitely non-zero map. So that's that. So we have the same structure as before. And now in decomposability, it's just right here. R3 is decomposed like this, U plus W. All right? Let's proceed a little bit. Don't look at homework. So how is this proof goes? Suppose this happened, right? Suppose this happened. Let me just say this. U and W are indecomposable subspaces, right? When I say that, it assumes it's invariant spaces. Right? So what is the next thing that we have to take care of? Suppose, period. I said something about eigenvector. Remember? Right. Does not have an eigenvector, right? So say W has no eigenvector. But once it does not have any eigenvector, what nice thing happens? How is that possible? Why is it? How can I assume this doesn't have an eigenvector? How can I say this? Why can I say W has no eigenvectors? There's only one, right? So one has it and the other doesn't. So once I have no eigenvector, what nice condition was there? Knowing that W is invariant. Something about m minus 3i, remember that? Stick it and hold subspace W, and what happens? It just permutes and don't kill anything. Remember that part? It goes right there like that. So, if you hit m minus 3i 3 times, what's going to happen to W? According to that, it's going to remain W, right? But we saw that, well, nothing will survive after 3 application of this one, right? Contradicts what we have found up there. 3 on 0 as the matrix. Everything is 0. All right? So that's why this one is indecomposable. So whenever you have this structure pulled out, that whole space is indecomposable. You see what's going on? You have a one eigenvector, pulling it back again, and pulling it back again, right? Because of the finite dimensionality and linear independence, which was the advanced homework problem you turned in today, this should stop. This pulling back procedure should stop, right? Every time you do that, you get linearly independent vector. If it is a finite dimensional vector space, it must stop. So you do that as long as possible, and that creates one indecomposable subspace, which is like that. So let me ask you this now. We show that this is an independent subspace, right? So one final question is that I'm adding it here. This is additional question. B is V1, V2, and V3. This B is a basis of R3, correct? And I'm going to compute MB. Do you know what this MB is? Who can explain what this MB is? M was that matrix with a negative 18. What is it? Change of basis, right? Right, it's a new system. So how do you calculate this? We want to calculate what happened to MV1, what happened to MV2, what happened to MV3. That's all you need. If these are the bases, right? You calculate this one in terms of V1, V2, V3, then you can write down a new matrix. That's a coordinate system, right? So who remembers about MV1? Right, we don't have to deal with any numbers. That's what I'm trying to write here. You don't have to go through actual numbers. We already know this one. So what do we know about V1? Is what was 0? This was something was 0 here, right? What was the matrix? M minus 3i. So let's use this one. What does this say? MV1 equals 3V1, right? So this is going to be 3V1 plus V2 plus V3, right? What is the coefficient? 0, correct? And 0. So 3, 0, 0 is going to be column vector, right? As a coordinate system. Let's do next one, M minus 3i. V2, who remembers this? That was V1, remember that? That's how we found this thing. So let's expand it. MV2 is negative 3V2 is equal to V1. Is that right? If you expand this. So what is MV2? V1 plus 3V2, right? So I'm going to write it like this. V1 plus 3V2 plus 0V3. All right? Let's do one more. M minus 3i. V3 is going to go to V2. Remember, that's how we found this V3. It's going to be MV3 is minus 3V3 is equal to V2. Right? So what is MV3? 0V1, 1V2 plus 3V3, right? Now, I know what happens in to V1, V2, V3 when I hit it with M, and these are the coefficients, right? So what is the matrix MB here? This coefficient goes to column vector, correct? The second coefficient, 1, 3, 0 goes to column vector, and the third one, 0, 1, 3 goes to column vector. So those one right above the diagonal came from pulling it back of this m minus lambda I business. All right, so we started with this matrix with a negative 18, and this thing, if you choose bases wisely, like this, and the matrix become like this, right? From here, eigenvectors, eigenspace, and indecomposability, all that was really computable by hand, right? So this is we're going. If I have in general a vector space like this, we want to go down to this business. This much of this is indecomposable, and M is also so that's a base change that do that. All right. Even if it is an abstract vector space, you're going to do it like this. All right. V1, V2, V3. You try to pull it back as much as you can, and you started with a V1, right? One eigenvector. Try to pull it back all the way until you cannot do this anymore. Then that creates one indecomposable subspace. All right. So this is the principle, right? So I can go apply one more, is m minus 3i squared. The same w is m minus 3i w. Is that right? I applied one more m minus 3 to this equation. But this m minus 3i is again w back. Right? And if you hit it one more time, you can conclude if you apply 3 more times, doesn't matter, 2015 times, it's going to remain invariant. Not just invariant, it's a permutation. Nothing is get killed. W goes into and onto the W. that contradicts the 0 thing that we calculated. All right, that statement part B doesn't contain eigenvector invariant. That's kind of standalone statement, right? It has nothing to do with this particular context. That's why this contradiction doesn't contradict anything. Does that make sense? that statement is a general statement. All right, this is very, very important result in the linear algebra, that you understand this structure, this space change, whenever there's insufficient number of eigenvectors, and this is the best we can. This is the best simplification we can pull out. So this is the upper diagonal, upper triangular matrix, right? And one section is devoted to, in our book, in the chapter 5, to explain to you everything can be upper triangular, but I did a little bit more, right? I could pull lots of 0 off diagonal. So why not? It was just right there, so I pushed it to this level. How was it? Is that all right? So probably one of our homework is that I don't give you this instruction. You go to do all by yourself, but it's there. You can imitate. You can use a calculator to compute this echelon form and things like that. All right. Okay. So let me state that as a proposition there. It's important statement. Proposition is that in this context, t minus lambda I vk plus 1 is vk for all k1 through, I think I wrote l minus 1. You know what I'm doing? They're pulling that structure, and I change m to t, right? So we play with the matrix. Now I'm just discussing this in terms of t and no matrix. We suppose this is a situation, and one more is that t minus lambda I v1 is 0. There is no matrix. We happen to have this chain of vectors, L vectors, that are in this situation. Right? What can you conclude? Number 1, v1, v through vl are linearly independent. Does this one ring a bell? Wasn't that the homework problem? Like this is like S, right? It's a chain of this. This was the homework problem you guys turned in today. So I'm not going to answer right now. But next time I'll answer that. But what's more interesting is that the subspace W generated by the span of this V1, V2, VL is what? What do you think? According to the whole thing that we go through right now, hope this summarizes something. There's no matrix, just this property we have, a chain of vectors. They're linearly independent. What can you say about this W, which is generated by these linearly independent vectors? All right, let me dribble back. This is what we were just talking about. Looks a lot like it, right? There we talk about V1 goes to V2 go to V1. Instead, I have T's, right? I have this condition and no eigenvectors. I get that part's unclear why this one has only one eigenvectors. But that's one connection you have to make. This one contains only one eigenvectors. Maybe I should state it as a 1.5. W contains how many eigenvectors? One linearly independent eigenvectors of lambda equals 1. With that, we draw some contradictions, right? What was the conclusion after the contradiction? If it does not contain, right, I split this one into U and W. If it has only one eigenvector, one of the components is not going to have an eigenvector. Remember that argument we just went through? From there, what was the conclusion? Change part of it. That's right. Indecomposable, right? If you split it further, one of them will not have an eigenvector because there's only one eigenvector. And if you keep hitting this t minus lambda I, then something's going to survive. Then it makes no sense. All right? So what's the word? Indecomposable. If it splits like u1 and u2, no, you split into two pieces. If it is split into two pieces, then it's going to be decomposable, right? One of them doesn't have an eigenvector because there's only one. If this one doesn't have an eigenvector, if you keep hitting with the t minus lambda I, what happened? It survives forever. But if you do it here, how many times? L times, everything will die. That's a contradiction. Right? If this one doesn't have an eigenvector, if you keep hitting with the t minus lambda I forever, this will survive forever. But according to this chain condition, it eventually dies. That's a contradiction. Therefore, it cannot be split into two invariant subspaces. Therefore, it's indecomposable. All right? That's most prominent, actually the only example of indecomposable spaces over complex scalar field. Everything breaks into these pieces. All right. Any other question about this proposition? All right. Right. Do you think it gives you a sufficient idea to how to go about and pull out one indecomposable subspace? So let's think about an algorithm. Find some lambda. This instruction makes sense? Right. If I give you some abstract vector space, just like that 3 by 3 with 18 and 9 in there, let's figure out one indecomposable subspace in it. That case, it turned out the whole thing is indecomposable subspace, right? So this W is indecomposable subspace. This is the idea. So find some lambda, an eigenvector v1, right? Inside where? E lambda. Is that okay? We know how to do this, right? So you find that, then what do? Keep solving something, right? Keep solving. What are we solving? This thing here. We started with the v1. That is the eigenvector right here, right? You find v2, you find v3, you find v4, but keep pulling it up by this t minus lambda I business. Keep solving. What's the equation? Lambda t minus lambda vk plus 1 equals vk. v1, look for v2. v2, look for v3. If it's finite dimensional, this stops. Do you know why it stops? Because those things you're finding is linearly independent. It keeps getting you one more dimension, one more dimension. If it's finite dimensional, it stops. In that conclusion, the linear independence is crucial. Correct? So it stops. So it eventually stops. So you collect them. That space you created here is indecomposable. Right? And span of what? The V1 through a VL is what kind of subspace? An indecomposable subspace. Okay? That's how you go and find one indecomposable subspace, which rely on existence of what? One eigenvector. All right? Does the algorithm make sense? No. So let's go back to that problem. Suppose you didn't know anything. You go for one eigenvector in here, right? You found one, correct? And keep trying to pull it up, and you got this third one, you realize that you have 3 linearly independent. You don't have to pull it back and try to solve it anymore. You will see that there's no more solution. You already have 3 there. So V1, V2, V3 makes indecomposable subspace, which happen to be the whole thing. Correct? But maybe if it could be smaller, then you have subspace that is indecomposable. Is that right?